So thanks for the invitation and thanks for having me on. Quick introduction about myself. So my name is Aravind. I run a company called TerraWatch, which I will talk to you in a bit. I come from a different type of kind of background. I guess a lot of people here are researchers, postdocs, kind of working more in the intersection of science and technology. So I'm more coming from the commercial side of things. I run a consulting firm, so I operate kind of in the intersection of technology, business, and science. So kind of an intersection of the three. So a lot of what you're going to see today is, I'm not going to present a paper, or I'm not going to present the results of a paper. I'm most, going to present and talk about trends in the area of course, edge computing, GeoAI, and let's say combination of them related to Earth observation. And yeah, so really today's talk is really a summary of what I'm seeing in the market, but also what kind of let's say the future looks like for Earth observation from at least from an intelligence standpoint. So to quickly kind of give you an idea of TerraWatch. So essentially, we are a consulting firm. I think some of you may already know the newsletter. So I write the newsletter that provides insights and analysis on the Earth observation market. Again, very much from a commercial standpoint. The focus of the newsletter is very much, kind of covering the trends and what's happening in the industry and how to, look at the industry where, what kind of applications are coming out for Earth observation. And of course, a lot of my work and the business is very much focused on consulting. So we do a lot of strategy, policy, and economic related consulting. And the focus of the consulting is very much on, go-to-market, market analysis, commercialization, business model. So a lot of commercial focus. And then we also organize events. Our event is called EO Summit, where we have a lot of users of Earth observation, so end users in insurance and energy, agriculture. So really the end users who are consumers of Earth observation come and talk about their use cases and their case studies. So that's kind of mainly what TerraWatch is. And of course, we've worked with public sector, private sector, end users that are users of the data in energy and, et cetera, a number of industries. So that's quickly about, TerraWatch and kind of where I'm coming from. So I guess I want to kind of start with a quick context in terms of where we are, and then kind of get into the discussion. So as you can imagine, we have a lot number of satellites that are launching over the last few years. The number of satellites is of course exploding, and it's leading to contributing to what we're talking about from a GeoAI standpoint. There are some numbers here. Of course, you can see the graph and you can see the trends. The number of satellites are going up. We are downlinking more data than we have, ever done before. A number of countries are launching their own sovereign constellations. So you may have seen, whether it's in Italy, Greece, Portugal, in the Middle East, in Latin America, in Africa, Asia. So, it's really all over the world, mostly derived from geopolitics and kind of need for sovereignty. But again, that means that there is still going to be more and more data in the coming years. And of course, over the last 3-4 years, we've seen, explosion in number of foundation models, both from the public sector, from the private sector, from nonprofits. So, a lot of, changes happening in the market. And of course, a lot of that is very much focused on open data. So, needless to be said, whether it's from Sentinel, Landsat, or MODIS, and, open data that is available, that's kind of where a lot of the models are derived from. But then, of course, there are also models that are, taking in private data as well. So talking about private data and private data providers, we know that there's, a lot of number of companies that are launching Earth observation satellites. So it's very hard to kind of keep track of everything. There are, this number just keeps on increasing across different sensors and modalities. So you see, a lot of logos here, a lot of companies that are launching different types of satellites with different sensors meant for different applications. Some are more specific than others, infrared, maybe for wildfire or for thermal related to water and agriculture. So I guess the applications are very diverse. But that's not the point of the conversation today. I'm guessing a lot of people here already know the kind of variety of applications. So I'm not going to go into those details. But the key point is that the number of satellites that are launching is exploding, and we have more data available than ever before. But then if you were to kind of look at the Earth observation value chain from data to all the way to application, there's a long gap. There is a big gap, and I think part of solving that gap is kind of where a lot of the effort over the next decade is going to go through. And one technology that potentially looks like an enabler in terms of converting the data into analytics and analytics into application is edge computing. So I wanted to kind of touch on edge computing and probably talk about a little bit about how that kind of oh, I hear a bit of an echo. I think no, it's fine. So I guess edge computing is kind of one of the technologies that is going to kind of enable us to bridge that gap between data and analytics and analytics and application. And you've heard talk about edge, and I guess there's such a diverse kind of group here, but hopefully some of you already know what edge computing is. But then for kind of those who are more in the different type of vicinity, so you can kind of think about edge computing as there are three kind of ways where you can think about intelligence related to Earth observation. One is very much ground first. So you have all the data that is downlinked. That's the traditional way. You downlink everything, and then you process on the ground. So all the process is on the ground, and then you have some level of middle layer where you have some limited onboard processing. So you can think about some filtering happening, some compression happening. Then again, there's very much in demo stages. We already have a couple of satellites, including FESAT, but also a few others from private companies that have demonstrated this onboard processing. But then also there is complete onboard processing where all of the data generated is processed, detected, and downlinked as analytics. So it remains conceptual. We have had some demo missions, but then we don't have entire constellations that are completely with onboard processing. We will have a few of them launch in the coming years, including from companies like Planet, and including a few other national constellations that will have complete onboard processing that are working across multiple applications. But we've already started seeing demo in that range. So as you can see, the level of architecture that we're building towards is going to be very, very different in the next decade, because we are investing in kind of constellations that are very edge focused, where the third category is where a lot of the focus is. But then you also have technologies that are coming in that are making the first category also very exciting, because you also have optical downlink, optical links that are becoming available, which obviously make data downlink faster, which obviously means that do you really need to process in orbit? Why would you need to process in orbit if you can downlink everything very quickly and very securely, because it's laser comms? So you kind of get into an architectural question of what does the future look like? Is it going to be very edge computing focused, where we're going to process everything on orbit, or are we going to go in the first scenario where because we have laser comms, you have with optical terminals, you can downlink everything that you're collecting very, very fast, because of the high bandwidth capabilities of optical terminals. So the question really becomes kind of an architectural choice of, are we going to go in this direction, or are we going to go in this direction? And of course, we'll probably end up in some sort of a hybrid, but it's an interesting question to ask, where if you're thinking about developing new types of intelligence or new type of applications for the edge, in 5 years, is that going to still be the case? Will the processing be happening on orbit, or will we start downlinking it, on the ground, because it's easier and better to downlink on the ground? So I guess that is not clear, but I guess that's kind of where the trend is going in terms of looking at it twofold. I talk a lot about edge computing, but then to really quickly talk about what edge computing really means, I guess for a lot of you this is very obvious, but then for those who probably haven't kind of work on the edge side of things, it's important to kind of appreciate that edge is not one thing; it's many steps, and I think it's important that we do all of these steps in order for it to be a complete onboard processing pipeline, because this is what we do on ground, right? Like we do a lot of calibration. So if you don't do calibration on orbit, it's going to have an impact on the results and the efficiency of the results and the performance of the sensor. So I think all of these steps becomes useful. So to just go through them quickly, you have acquisition and going from collecting the data to onboard calibration. in order to actually calibrate your data against perhaps another instrument. Filtering, where you don't want cloud-related images or you don't want empty terrain. You kind of filter it on orbit. You compress it. Of course, compression becomes very useful for sensors like hyperspectral, where you have a lot of volume of data because hyperspectral collects data for different bands. So you just end up in a 100 gigabytes to a few hundred gigabytes very easily. So you need to compress it before you downlink. And then of course there is the inference step, which happens in some cases with the model that is already on the satellite or is updated regularly, whether you're detecting or classifying or extracting features. That's where mainly the inference happens. And then the important question is what happens after the inference, right? Like, does the inference actually lead to something that is another task? Is the inference actually leading to the command that's going to send to another satellite to take a higher resolution image? Or is the output really just downlinking, whatever the detection was? I found a wildfire, there is a thermal hotspot, you just downlink the location. Is that the output? Or is that going to be a command to another high resolution satellite that's probably coming, in the tail, in order to take a very high resolution image of that area, right? So I think that kind of architecture, again, is being built, is being demonstrated from companies like Eurotech, but also a few others that are kind of working on this, end-to-end architecture in order to have this, let's say, this approach becoming more and more feasible. So it's just a quick idea of what edge computing is. When we talk about edge computing, it's also important to talk about why edge computing matters and where it matters most. You might have seen there are some applications where it's more useful than others, and then there are some that are not probably going to be the highest of use, at least for now. Maybe, when we have orbital data centers, if it works and it's economically feasible, 10 years from now, maybe everything will become possible in orbit. But for now, edge changes the game in only three things. One, is it time sensitive? So it's wildfire, it's oil spill, you're tracking a vessel, illegal fishing. Of course, if it's time sensitive, the value is very easily understood, because you don't have to wait to downlink the data, process it, and then get the insight. You can just get the analytics directly. And the second one is if you want to selectively downlink, meaning if you're a satellite operator and you want to save costs and you don't want to spend a lot of money downlinking unnecessary imagery, like, something that's filled with clouds or with empty oceans, you can just discard it and not downlink it. Second use case. And the third use case is, as I mentioned before, autonomous tasking, where the satellite, does the work, as an analyst, and then sends an autonomous command to another high-resolution satellite, for instance. So this is kind of where I think edge is going to change the game. But then there are use cases where I don't think it's going to have a very big impact, mainly because of the level of complexity of the task, not because it's not possible. It's more because of the level of complexity and the need for high accuracy. If you're trying to do very, long-term mapping, you're using Landsat for a 50-year data set in order to kind of do a land cover change or an urban change, application. That's probably not the, best use of edge computing. And same goes for any sort of scientific application. So you're trying to, estimate soil moisture. Yes, you can estimate it with a limited data set. Maybe you're using a sewer band and you want to, detect soil moisture on the ground. It can, but you know that the best form of soil moisture is probably derived from, multiple data sets, fusing it together. So, unless that is feasible, it becomes very hard, and it's very hard to do with edge. So edge computing does not really add value in that case with a scientific application. Or if you're trying to do some sort of complex multi-temporal analysis, I don't know, something like you're trying to monitor the change in the, in the ice sheet that is getting out of the, one of the, either the polar regions of the world, and you're kind of tracking it over 15 years. And you have to kind of, notice the change over a long time frame and do that multi-temporal analysis. Again, it's probably not the best use of edge compute. So, you kind of have different ways of thinking about edge compute and how it adds value. And to summarize, I think essentially edge AI enables really three things, as I mentioned before. You take the data, you calibrate it, and then you compress it, and then you downlink it, because you just want to downlink smartly and only things that that matter. Or you have, of course, onboard detection. You detect a wildfire, you just downlink the analytics directly. And then, of course, you have autonomous tasking where you can send the command to another satellite. So on the whole, this is kind of what edge compute is enabling, and this is kind of where the industry is going towards. But we have to also talk about things that are happening on the other side, right? Like things that are happening on the GeoAI side. And I guess what's happening on the ground has implications on what's going to happen in orbit, because it's going to be potentially the same model that's going to run on the satellite. Or maybe it's going to develop more in a competing fashion, right? So it's interesting kind of talk about how that convergence is going to be, the convergence of GeoAI and edge computing. And of course, we also need to talk about fusion, because unless we have proper multi-sensor fusion enabled, whether it's on the ground or it's on the edge, we are not going to be able to process data. And as we know, one sensor is not enough, and I'm going to talk about that. But some people already know that one sensor is not enough, so you need to fuse it from different data sources. So, we are kind of looking at a future. Again, this is more of a, let's say you can think about it as a 10 to 15 year, like a timeline, where we are looking at a convergence of edge and GeoAI, right? So of course, with combining edge and GeoAI, you can kind of start to do a lot more things. You can make the satellite more into an actual analyst than just a camera. So if it's just a camera, yes, you can do a little bit of filtering, but you can't really do, full on processing in orbit. Of course, with GeoAI, you can do a lot of processing in orbit, whether you're detecting and classifying changes, or even generating embeddings, right? Like you can generate your embeddings directly from orbit and downlink directly the embeddings. So potentially that's going to be possible. But of course, that for this, a lot of things need to come true. Before it was all based on rules, right? Like the rules is, if the cloud cover is less than 80%, don't downlink, right? So that's more rule based, but then you can already have a model decide that rule. You don't have to, hard code a rule in your satellite. You can actually have models, and of course, continuously update your models, which can then decide what's going to happen. And of course, that has an impact on what the output is. In a normal case, it's probably still raw data that you're downlinking for better processing, but in the future, we'll probably have more analytics-ready products that are, ready for further analysis, right? But, I'm talking about a future where I think a lot of things need to work in order for this future to be possible, right? You need to have, of course, all the data centers, because, I'm talking a lot about GeoAI models, and I'm going to talk about GeoAI in detail in a few slides. But as you know, training data is, you can't really store a ton of training data on satellite. Maybe in the future, when satellites become, larger, and let's say Starship becomes operational, you can have a larger satellite potentially, but still, how much training data can you really store? How much labeled data can you really upload to a satellite? So you need potentially some sort of a data center in orbit in order for this future. Of course, you need better space computing hardware. We saw NVIDIA launch their new, space hardened chips, I think a couple of weeks ago. Maybe that's a start, but still there's going to be a long way to go before we get to a stage where we can process whatever we want in orbit. We're not there yet. These are probably, stepping stones for us to get there. And of course, in order for this kind of future architecture that we're talking about, we also need, full, intersatellite links, which again are starting to be deployed, but we need them kind of become the baseline for all satellites, right? So for imagining this future that we're talking about, we need a lot of things that need to come true. So that's a lot more kind of futuristic than, what it is, but it's interesting to see where we can go in the future. But as I mentioned before, we can talk about a lot of things, but then the reality is that you need to have sensor fusion that is, possible or enabled, and it's not easy. And first of all, we already know why one sensor is not enough. Whether you're looking at optical, of course, it's clouds. If it's SAR, it's hard to interpret, and if it's hyperspectral, there's a lot of trade-offs on which bands you look at. So as you know, there's one sensor is never going to be the answer. So you need to be able to fuse data from different sensors. So, but how much of kind of a task it is. It's not an easy task. There's a lot of work that needs to happen. Fusion requires a lot of things. Fusion is not easy. Probably some of you already know a lot of this, but it's important to realize that people can say, why don't you just fuse dataset 1 with dataset 2 or sensor 1 with sensor 2? But there's a lot of things that need to be there in order for that fusion to be possible, because unless that fusion is not possible, we are not going to be able to get to a model that can do everything that we wanted to do in an accurate way. Of course, the fusion, we need standards, which, as we know in our industry, that's, there's still a very kind of slow progress in that, availability of standard, mainly for comparison and integration. As some of you already work with HLS, Harmonized Landsat Sentinel Data Project, and we need a funded project in order to create a data set of a similar type of data, right? Like Sentinel and Landsat are comparable data sets. But then in order to make them comparable, there's a lot of work that needs to go in. So imagine now, doing that for other modalities and data from other providers. It becomes very, very hard, and it's not an easy problem. And of course, you need common reference frame. You need, of course, the data to be aligned spatially and temporally. It's not going to happen unless, somebody actually works on it and creates a standard for it. And same goes with calibration and validation. So especially if you look at combining data from a commercial data provider and a Sentinel, you need to kind of know the uncertainties and limitations of that sensor, whether it is data from a private company that launched its own sensors. And even if it's the same sensor, same electro-optical sensor, you really need to kind of understand, the calibration it has gone through in order to then be able to fuse it with a Sentinel. So calibration and validation can not taken for granted. And then, of course, lastly, you need the infrastructure. It's easy to say, we can fuse dataset 1 and dataset 2, but unless you have infrastructure, your compute costs are going to go, and grow and explode, especially if you're thinking about cross-model analysis. So fusion requires a lot of things, and I think a lot of, people who talk about fusion probably take it for granted that a lot of these are actually available, but then a lot of work happens, and a lot of investments happen across all these areas in order to make it work. So fusion is important. So when we are talking about GeoAI, which we're going to talk about, it's important to remember that a lot of work kind of needs to happen in order to kind of moving towards a world where a lot of this potential of GeoAI becomes possible, whether it's on the ground or it's on orbit. Of course, on the ground was the first step because it's easier. So to end with, I want to kind of talk about GeoAI, because I talked about GeoAI in the context of running it on orbit, but then how does it look like on the ground? Because on the ground, this is not a solved problem, right? There's a lot of, of course, there's a lot of developments that are coming in. Of course, ESA is doing it, NASA and IBM are doing it, Google is doing it, and a number of other private companies are doing it. Nonprofits like AI2 are launching their models. So there's a lot of models coming in. But then it's important to remember that this is also not a solved problem. So before we talk about running GeoAI models on orbit, we also need to realize that we have a lot of work to do to get the GeoAI, let's say, approach working on the ground. So I'm going to talk about a few things from more of a realistic perspective on where things stand. So first, I want to talk about hype versus reality, right? Like, we are at a time where there's so much hype and so much talk about what geospatial models can do, foundation models can do, and there's a lot of talk about what is possible. But I think there are potentially 5 things that are kind of reflecting between the ambition and the reality. So, of course, ambition. We are talking about this one global model that is trained on every type of data that is there, that can answer anything that you want. You can ask any question and it's going to be able to answer. It's a good ambition to have, but then the reality is that, I'm sure some of you are already working on it and know what I mean. You need to go and fine-tune your data. You need to account for local conditions depending on the area that you're looking at. The availability of data is not common. I'm going to talk about that in a bit. And of course, there are contextual nuances. The fields in Africa and Asia are not the same in fields in Europe and North America. So it's like a lot of fine-tuning that happens. So that one global model that we're talking about is a good ambition to have, but then that's kind of the reality. The second thing is, you can use this one model for every use case that you're thinking about, crop monitoring, flood monitoring, infrastructure monitoring, everything you can do with one model. But then really, the truth is that a lot of models struggle with diversity into what is even considered a house, what is considered a crop, because as we know, there's a drastic difference across geography, across culture on what things look like. And related to the third point, the scalability is supposed to be there. It's supposed to work across all parts of the world. But then the truth is that the training data sets are are concentrated in some parts of the world, mostly in the West. And as a result, the models don't perform where they are potentially going to have the most impact. They don't perform that well. There's a lot of initiatives in place to kind of develop these models. But then the truth is that one model that everyone talks about is kind of getting hard to kind of use for every use case in every part of the world. And of course, like I said, the potential says that this model can be transferred for any application. You can use it for any use case. But then the truth is that the domain adaptation is a manual piece of work. Models are fine-tuned with curated data sets by experts. If you're agriculture, folks working in agriculture are creating that model to make it work in agriculture. So yeah, I guess the whole kind of ambition is a long way away in terms of looking at reality. And then the last point is, I think, probably more related to the actual satellite data itself. You probably know a lot of satellite data that is available is not AI ready. I don't think we have a definition for what AI ready is, but even if we assume a very simple definition of, is it going to be ready to be integrated into a model? Not all of the data sets are in the same level or in the same condition. Hopefully we will get to a definition, soon. But the truth is that today, if you were to talk about that global model, the global model will have the ready data set. But then today, the truth is that whoever is the user is doing a lot of the pre-processing work in order to make the data AI ready. So that's why there's a long gap between what the hype is and where the reality is standing today. So essentially, that's kind of a quick overview of like the 5 gaps. And I also think this is related to 5 barriers, which I will talk to you in a bit. So before we kind of look at the barriers, I wanted to kind of think about a quick definition for what GeoAI that is actually decision ready could look like. And after working with a lot of users in the community and kind of talking with a lot of people, I felt like the definition of what a decision ready GeoAI tool or model, I think it requires 3 things, right? Like, of course, these are very obvious for a lot of you, but I feel like those 3 things are important for every model being developed. The model needs to be trustable. Of course, it needs to give the same kind of results and it needs to be independently verified. It needs to be explainable, because the value of GeoAI is that if you're a non-expert, you can come and ask a question and get your result. But unless that non-expert is able to understand how it told you the result, he's not going to trust this model for the decision. It's the same thing like how we use our clouds and ChatGPTs of the world today, because sometimes we don't know how it came to a conclusion, and if we don't know, we are not going to trust the output. So imagine someone in insurance or someone in government using the same model. And if we really want this to be successful, we kind of need to focus on explainability. And then the last part is, again, usability. If you're talking about making non-experts use, we can't ask them to pre-process and input data that is only high quality data, or it requires a team in order to make it work. It needs to be directly usable. And I think a lot of GeoAI tools that are available today are meeting only one of these, or maybe 2 of these. It is not all 3. And I feel like if we were to get towards a future where GeoAI is scalable and it's running very well on the ground, it's important that all 3 are kind of met. So I want to quickly go through like a couple of barriers that I feel like GeoAI it needs to address in order to scale, and I'll go through them quickly. So one is data readiness. As you know, I think some of you already know, the foundation that we are starting with is very uneven. Data quality is very fragmented and consistent. There is, of course, licensing friction, especially if you want to go into commercial data and global coverage. It's not really, again, even, because the data is available in different forms in different parts of the world. So data readiness is, for me, the first barrier. The second barrier is more related to AI readiness, and I told you this before. So as the graph suggests, or the visual suggests, the user has to do a lot of work in order to make things work before he can actually create an application. But AI ready is potentially where the user does not have to do a lot of work because the data that is arriving is already ready to use. So he can just go and fuse it with different data sources and then get to his application. So essentially, the time it takes for a user needs to kind of shorten. If we were to make GeoAI work. Number three is related to models and embeddings. So I think we can talk about it on a whole presentation. Maybe you have already talked about it. For me, models and embeddings, foundation models and embeddings, I think for me represent a big kind of improvement and change in the way geospatial industry works. But for me, the problem with both of them is really in common, coming back from its closed nature, right? Like it's very opaque, it's not transparent. Of course, there are a couple of models, where, for example, from ESA, but also from other parts of the world where models are open and it's not completely closed. But then even if they are open, how do we know this can be trusted? Because benchmarks are good, but then benchmarks are good for evaluation from a technical perspective. But then if you're talking about a user who is a non-specialist, he will not understand the benchmarks. So as a result, it kind of becomes a problem in how they make use of it. So I almost feel like there are building blocks through foundation models and embeddings are there, but then they are kind of fragmented and they are not connecting to where the user is. Last, I think there is a gap in productization. So essentially, there's a lot of research that's happening in GeoAI, of course, on an R&D basis or R&D style. As I said, there's a lot of foundation models today. Every week there's a new one coming in. So research, there is no problem. And using these research tools, there's a lot of bespoke projects that are happening. People are using these models for like specific clients, for specific applications, but then that is not generalized, meaning a lot of transferability is not there. Meaning, if you were to think about a product, like, is this a product that uses GeoAI in the background that a non-specialist can use? There are not many products that are available. So I feel like we have a long way to go before we can get to stage 3, where we actually make products that are based on GeoAI, but actually used by non-specialists. So I feel like that's another barrier that we need to solve if we were to make GeoAI work on the ground. And last thing, I think it's more to do with structural barriers. This is more of a controversial one, where I feel like even though you have the most amazing model and the best data available, I don't think it's going to be enough because number one, the cost to participate is very high. If you don't have access to GPUs or some form of credits, nobody is going to train another model, and it's still very expensive. And it also means that a lot of parts of the world are not doing it because they cannot afford it. Number two, I think there's a lot of duplicated effort. I think there's no shared starting point that everybody is going to start from. I think what you're working at PhilLab, but also what a few other organizations are working on, is to help establish that standard, let's say, starting point that everybody can start from. And I feel like that's still a big problem in terms of fragmentation. Number three, there's a talent gap. There are quite a few, options and job options available if you're looking at it from a job perspective. But even from a research perspective, there are not many people who are well versed in all the 3 domains, right? Like, you need to have some sort of geospatial expertise. You need to have some sort of machine learning expertise, and of course, you need to have some level of remote sensing expertise. And I think unless you have all 3, you probably will not be able to handle everything that is required for making GeoAI work. And fourth point is more related to kind of politics and kind of how privacy concerns are keeping a lot of the data siloed. So it's not going to be easy to solve that. Some data sets are locked, maybe locked for the right reasons. You cannot do anything about it. So even if you have the best model and the best data available, if you want to continuously update it, some data is not going to be available for you. And then the last point that is more to do with how I think the academic community operates is, today the academic community rewards papers and publications, which is great. But I don't think that is actually leading to any products in the market, which is also why I think especially in our industry, I feel like there's so much work that is done on the R&D side, but that is not kind of moving to actually closer to impact, because there's a big gap between how the incentives are. Your incentives are, especially in academia and research, very much aligned towards publication more than the product or creation of a product. And it's starting to slowly change, which I'm very glad about. But there's still a lot of gap between taking all of these amazing research work and kind of making it into a product. So I feel like there are some barriers that we need to cross before we get to this world that we're talking about in terms of GeoAI on the ground, and of course transferring that to space by processing data on orbit. So I'll stop there. Thank you for the attention, and hopefully it was interesting. Thanks.
Nice. Thank you very much, Aravind, for the super interesting presentation. It's nice to have this kind of broad overview with insights about the whole sector, let's say, in kind of contrast with some presentations we often have that are very in depth on one very specific technical topic. So that's very, very refreshing and insightful. Does someone here have a question, perhaps? If you are open to answer questions, of course.
Broad one. It's about more of TerraWatch. On which aspects do you support the companies and organizations that you mentioned at the beginning? Is it more about the applications themselves, or the strategy, or I was just curious on which aspects you would support the companies you mentioned at the beginning.
Yeah, it's very much from the application standpoint. So a lot of companies, the companies have different type of needs. Some companies are interested in, helping understand how Earth observation can help understand their supply chain risks better. Because they want to understand, for instance, level of asset level climate risk, for instance, or supply chain risks, which again is probably more important today because of what's happening in the world. A lot of risks for a lot of organizations. So it's very much focused on how Earth observation can help solve a problem for a lot of these organizations, and essentially kind of problem solving together with them, because in some cases the technology exists, but the answer is not very easy. It's easy to say, to take an example, they are interested in changing their supply chain because, I don't know, some part of the world are more susceptible to climate risk more than others. So in 10 years they should be ready to change where they source their crops, because in that part of the world the crop yield is going to change. But then that's good information to have, but then they need to kind of actually be able to figure out what crop, what part of the world, what is the level of risk, and how it affects the organization. So there's a lot of questions. So Earth observation can give you a signal or a variable, but then that still needs to be connected to business. So I think a lot of our work comes from taking the output of Earth observation and kind of connecting it to a business process or a business requirement. So a lot of, let's say, taking the application and actually making it into something useful for the organization and helping them understand that.
Okay, interesting. Thanks.
Someone else? I have a small question myself. If you in the presentation, when you talk about GeoAI, you kind of very quickly talk about foundation models and embeddings, which, I mean, there's of course a lot of talk about that recently in research, but and in industry probably. But doesn't that skip a whole a large amount of work with AI and machine learning that is currently perhaps been more used in industry, or that's at least what I imagine, which is more specific, task-specific models that are maybe at this point already more integrated into services and more deployed and more operational. Or yeah, what is your take on that? Or
yeah, no, 100%. I think for me, the the biggest value of what the foundation models today are going to enable is if you were to think of the use of Earth observation in kind of three phases, because again, people who are already using Earth observation will continue to use Earth observation if they already use an ML-based approach to, I don't know, detecting forests, deforestation, or for whatever use case that they're using it for. They're not going to change that, and I don't think there's any reason to change that because it's already a working working process. It's delivering results. So there's no reason to change what's existing. For me, I guess the hype, or let's say the promise of a lot of the foundation models and embeddings is making that group bigger. If you were to go and give this to an organization that does not use Earth observation, I think foundation models make it easier to try Earth observation, because before the foundation model era, let's say, they can still use insights from satellite data, but they need to hire a team. That team needs to develop a model defined for their use case. With foundation model, what is the advantage is that the model is not great, the model is not perfect, but then they can try it out. They can try it out to see, okay, so this is the kind of result I can get out of satellite imagery. Maybe it's completely wrong because the foundation model is not fine-tuned for this purpose, but at least they can try it out. And I think for me, the barriers is lowered because of what foundation model can enable. And it helps a lot more organizations and users discover. I have seen that in, for example, the humanitarian sector, where, for example, the Red Cross uses a tool like an LLM developed based on a foundation model, where they can go and ask a question and get an idea of how much this city has expanded in the last 5 years, for them to understand the level of scale required if that city were to be flooded, right? Like, they don't need accurate information. They just need to know how many houses were added in the city and which parts of the city were very well developed in the last 5 years. And that's their use case. Their use case is very simple. They don't need to download imagery. They don't need to process it. They don't need to understand remote sensing to get this answer. And just having this basic answer, I think, changes their approach and how they plan their operations, right? So, and they are a new user. So for me, that is the promise of foundation models, because it enables the development of applications. And of course, if they want very accurate, information, of course they need to fine tune it and develop it for their use case. But at least for me, foundation models enables this kind of lowering of barrier, which can help increase the impact of this technology. Because if we just keep it within ourselves and only experts can use it, I don't think the potential of this technology is realized. So for me, I think that's probably the good thing about foundation model. But then, of course, we need to understand the limitation of what is possible from these models, because, as you know, they are not great. They are not perfect. They are not comparable with, ML models, because they have been developed for years. So yeah, so I think, people who need to understand the differences will understand, but then someone who just needs a simple answer can just go and use it. So I think for me, that's the advantage of what this offers.
Yeah, that's interesting. So we should focus less on having them outperform all the task-specific models, but focus more on making them as accessible as possible. I mean, this is kind of baked into the very premise of the idea, but still, I feel like that is not always the main selling point of the research papers, let's say, that are more
100%,
focused on.
Yeah, I think they have to oversell it sometimes. So you have to oversell sometimes. So I think,
Yeah.
Sorry, Roberto has his hands raised, or?
Yeah. But finish. Don't worry, I can wait.
No. My question is done. So go ahead, Roberto.
Okay, so first thing first, thank you for the presentation. It kind of resonates with a lot of my ideas about Earth observation. My questions concern a bit more the commercial aspect, and I would be glad to have your point of view on this. Like, where do you see the greatest obstacles and opportunities for the commercial actors in Europe? And what do you think ESA should do to accelerate the development of a commercial space economy?
Well, I guess I think the simple answer, or the short answer to that, is we need a lot more kind of closer collaboration with the end user, whoever the end user is, private company, nonprofit, government user. We need to kind of have a closer collaboration with them, because I feel like there's a lot of, I think commercializing something that is derived from science is very hard, because science focuses on, let's say, perfection, and science focuses on, going deeper and deeper and kind of, finding more and more answers. But then commercialization kind of focuses on a very different, let's say, success criteria. Their success criteria is, does it help the organization make better decisions? And does it help the organizations make more money? If you want to think about it from a private sector perspective, or if it's from a non-profit perspective, is it helping them create better impact? So I think and sometimes there's the overlap, right? Like, in order to make more money or in order to make better decision, you need to have a very, very good product. So that's an overlap where science and commercial have the same, let's say, objective. But then in a lot of cases, science and commercial don't have the same objective, and you won't know that unless you work with the end user. So for instance, to go back to like AI and foundation models, or just Earth observation in general, sometimes Earth observation just saying, like I just gave you an example of a Red Cross example, but if you look at it from an insurance company standpoint, the insurance company just wants to know if this property has changed their roof or added another flow, because they want to know if they can charge this house more money because they added another floor or they changed their roof, and that's what they want to know. So of course, for knowing this, you can of course go very deep and create the best model that can use, for instance, SAR to look at the altitude of the change, or you look at optical imagery to look at the shadows to see if they've added a floor. So you can go super deep and develop something amazing. But then the insurance company just wants to know if there is a floor or not. They don't need the perfect dimension of what the floor is. So sometimes science's objectives and commercial objectives are potentially very different. And I think working with the end user and kind of understanding their requirements would help us create products that are commercializable. Because if we focus too much on the science, especially for commercialization, if it's a science project, then it makes sense. But then if it's a commercial project, it needs to kind of look at it also for what the user wants and develop something that kind of is closer to what they are interested in. Because if you offer, like, a good example is like deforestation, right? Like, you can develop a tool that can detect different types of species in trees, and tell you which tree has been cut down, what is the number of trees that were cut down in the last 3 years, etc. Great project to work on. But if the corporate company just wants to know what percentage of trees were cut down in the last 3 years, and they don't really care about the species, then you may have the best product, but they don't really care. They can just use a very basic product and get their answer, right? So I think that's why I guess it's important to kind of work more and more with the end user. And I think for me, that's what I think needs to happen more in Europe. And I think the advantage in Europe is that we have data open from Copernicus. We have Copernicus services. So services is open. We have the Copernicus data space ecosystem. So a lot of capabilities available for access by everybody. So I think a lot of building blocks are already there. I think if we work with the end user and kind of develop something according to their needs, I think we can commercialize pretty well and pretty easily, because a lot of the foundation is already there and we have a very good foundation. And the good thing is we all have access to that foundation. It's all open. So everybody can start from the same level and go from there. So nobody is going to be having a very, advantage compared to someone else. Everyone starts with Sentinel. Everyone starts with, Copernicus services. Everyone starts with CDSC. So the base layer for everybody is the same. So I think commercialization should be easier, because it's not like, someone has access to something that nobody will have. Of course, if it's commercial data, I understand, but then on a baseline level, I think everybody starts from the same level. So for me, that's exciting that we can do that in Europe with our Copernicus.
Yeah, I think it's a very brilliant idea. But in your opinion, do you think that we are underlooking some aspect of the downstream application? There are some applications that we are not considering in this moment that might be viable commercially.
No, I think there are not many new, applications, because for me the value of Earth observation is not going to come from new use cases or new applications. How are we going to make existing ones better? Because we are not going to create many new things. I think there have been some new things in the last 10 years. Let's say carbon markets. That was new, right? Like we looked at forests, we look at, stored carbon and biomass in trees. We looked at it before, but there was not really a commercial opportunity for that. And now with carbon markets, it's becoming available, and carbon markets already has its kind of share of troubles and history. But still, that was a new application that was unlocked. But a lot of applications, if you think about it, from you're looking at property for insurance, you've always done building detection, or you look at mineral exploration with hyperspectral, which is the new kind of sensor. But mineral exploration with hyperspectral was always done. So it's not a new use case. So I feel like a lot of the use cases are not new. They just need to be made better. So for me, the question is, are we going to make it better in the sense that, are we going to make it better compared to in situ data? Are we going to make it better compared to someone on the ground? Sometimes people may prefer to just send someone on the ground instead of detecting from remote sensing. So can remote sensing do that job better is for me the most important thing. So it's not so much about new applications, but it's From says there's an existing study by Copernicus which targets commercial and understand the gaps classified into it, covers 8 thematic areas. Okay, thank you. So I guess there's a lot of work that needs to be done. I also see a question on the chat, sorry, that I'm just seeing. Sorry about that. So Robert, from your perspective, what should a current master student in GeoAI concentrate on or deep dive in without focus on favorite topics? I know it's important to focus on something, but I want to exclude it from this question. Okay. What should a current master student in GeoAI concentrate or deep dive in? Well, it's not really a favorite topic. For me, the thing that does not get a lot of attention is how are we going to make the, pre-processing part easier. And I think that is not something that does not get a lot of attention. Like the application side gets a lot of attention, but I'm thinking about, a case, and I think it happened a lot in, for example, in the medical field, where there was a lot of unstructured data. And of course, it's very true of our industry as well. There's so much unstructured data from different sensors, different providers. And, if you think about combining a lot of these data sets, there is very, very little work. And of course, it's happening via space agencies. It's happening via, their own initiatives. But there is no specific solution for me that kind of focuses on what can we do to make it, better in terms of making that fusion possible. And I think I talked about it in the presentation, but I think that for me, the interesting thing, because if we were to kind of standardize the pre-processing, and if we have a simple solution, and in the future, if we have a framework that we can use to fuse different sorts of data sources together easily and in an efficient way, for me, that is going to help unlock a lot of potential of GeoAI. So it's kind of related to GeoAI. So it's not related to a specific application, because if you talk about application, you can talk about any industry, any application is interesting. But for me, this is something that, I think is probably potentially more interesting. So making, fusion work in GeoAI is probably what I'll say. I think I don't have anything else on the chat. So anything else before we close?
There was one more question on the chat, I think. But no, this may be more of a remark. Yeah, okay. I'm sorry. Okay. Does anyone else have maybe one last question? We have a little bit of time. Otherwise, I guess we can more or less conclude. Then I would like to thank you very much again, Aravind, for the super interesting talk and for the nice discussion and answers afterwards.
Appreciate it.
So have a very nice rest of the day, and let's keep in touch.
And stay in touch, everyone. Take care. Thank you.
We'll run into each other again later. Bye-bye.
Thanks. Take care. Bye-bye.